So Kathy Ehrig, what a rock star. Where do I start? I've been fangirling big time this week. Very excited to get her on. So yes, she's a super brain and lovely human, and I feel very lucky that she's here with us for the next hour or so. So she's been working at the Olympic Dam deposit for over 30 years. She's published more than 125 papers, in excess of 50 presentations, multi-award winner, including this year's Haddon and Forrester King medals. So it is going to be incredible hearing from her today about metallurgy. Mineralogy always matters. So it is going to be a great session. Please use the chat. We'll open up the floor and have some discussion at the end. And yes, thank you so much, Kathy, for joining. It's wonderful having you.
All right. Thanks, Jess. And we'll say thanks to your comedian. We'll find out. Just bear with me while I try to hook up things properly here. I see a lot of familiar names in the audience, so they'll say, "Oh, she's recycled some slides." Yep, but we'll put a very slightly different twist on it. We're going to talk about geometallurgy because I've spent a lot of time with that. And even though my name's up here only, I have a team of people behind me that support me all the time. And without all their efforts, these sort of things wouldn't be possible. And again, thank you, Jess, for inviting to present on GeoHug. We wanted to backstep a little bit, and greater than 50% of new mining projects fail. And what does that actually mean? It's that they don't achieve the design metal production within a few years. And that's our industry. And you have to ask, where do things go wrong? And they've been going wrong for a long time. In fact, the mining industry has a history of that kind of record. This slide here is mainly sourced directly from Peter McCarthy's 2014 presentation. And by evaluating all kinds of different mining projects, you could break it down to all the categories on spots they failed and assign percents to them. On the left-hand side, we see a whole list of things from mining design and scheduling, geology resources reserves estimation, and metallurgy test work, sampling, and scale up. And there's numbers associated with that. But when we get all of those things wrong, those kind of cumulatively add up to these failed projects. And as an industry, when we have these delayed startups, it's really delay on return on investment, and that means really money down the drain. And it's not only Peter McCarthy that knows that. There's a whole bank of people that work on this. So there's many other studies that say very similar things, and there's some references there. But it could be because we're all geologists here, and with some metallurgists I see in the audience, we're just going to focus on the geology and metallurgy side for a minute. And this is really the connection where Geomet comes in. Geomet will go across all those boundaries, but we're really just going to focus on the geoscience side and the metallurgy side for a minute. And what I'm going to do is just give you some overall discussion about Geomet and mineralogy, and then we'll do some specific discussion about Olympic Dam. So first of all, geometallurgy, there's all kinds of definitions out and about, but the one that I like most is from Steve Williams, who happens to be a metallurgist, is geometallurgy is the study of the drivers of metallurgical response that lie in the geology and mineralogy of the deposit. There'll be all kinds of other definitions that include the economics and all that, but let's just stick to the basics. So when we think about geomet and deposits, it's a big encompassing field, but what we need to go back down is to even the more fundamental components. So I'm going to list a bunch of what I call the axioms, these things that are self-evident, but we're going to state them anyway. That elements occur in mineral deposits as minerals. Minerals are mined, and metallurgy extracts elements from minerals. Mineral assemblages are the basis of rock deposit and alteration classification systems. You would say, yes, tell me something new. Minerals are variably distributed across all the ore deposits, and they're variable, and there's no exceptions to that. Hence, the ore characteristics will vary as the deposit is progressively mined and processed throughout its history. And there's one kind of big linking quote that I really like a lot, and it says, rock type controls throughput and mineralogy controls metallurgy. And for those that don't know, the quote's from Peter Monroe and Bill Johnson, who are metallurgical gurus in Australia and probably internationally. So this gets down, when I see each of these lines here, you say, there's minerals, 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 minerals. And when I talk about usually it's about minerals. mineralogy in our business always matters. And that means all the way from exploration through mining and processing and eventually the closure part of our businesses. Times have changed, as we all know, and then particularly those of us with gray hair could reminisce on how it was 20, 30, 40 years ago, but not really pertinent necessary to today. In the 20th century, we relied on assays and qualitative estimates of mineral abundances to describe characteristics of mineral deposits. Why did we do that? Because we didn't really have any choice. That was the only data that was available to us. So assays were often used for proxies for mineralogy. Bulk mineralogy could be done, but they were limited and very expensive, hence not practical to implement at the deposit scale. As geologists, we're very good at recognizing minerals, and our ability to create exploration models have been very successful for the discoveries. But they're absolutely useless for predicting and forecasting metallurgical performance at the precision that our modern mining industries will actually require. So we see some really antiquated microscopes there and a little bit more modern optical microscope. But then we hop into the 21st century, and there's been massive changes in technology. We all know that. But for the geomet side of the world, a couple technology changes were really significant. And assaying for almost the entire periodic table, the speed at which that could be done and the cost has dropped so much that it's available easily for exploration through to production. And here we're going to really focus on minerals. Because of that, we can do quantitative element to mineral conversions at the deposit scale. So where we only had assays at the deposit scale, we can convert those assays into minerals. There's been a equal change in our ability to measure quantitative mineralogy from the deposit scale all the way down to the nanoscale. And a couple of the instruments that we know are these automated SEMs, whether it be MLA or QuimScan or any of the other modern equivalents, and you think down at the microscopic scale. But then we also have measurement technology that allows us to scan core and hyperspectral space and a lot of other ones to get a lot more mineralogical information so that we can populate block models across the whole entire deposits. So what has this really brought to us? A mega increase in analytical precision or analytical resolution, the speed at which this information can be collected, dramatic reduction in the cost, and linked with a significant increase in computing power at our fingertips. And this is really transformational change for what we do. So we have this ability to measure minerals at the deposit scale, and we're going to embark on a geometallurgy program. So what do we actually really need to know? And the most important thing is that there isn't recipes for every single deposit. It's really, you have to have programs that are fit for purpose. What's fit for the company I work for is not necessarily fit for purpose for somebody else's company. It's also not necessarily fit for different deposit types. What I'm going to describe is something that's worked for Olympic Dam, and there are cross applications. But things we all need to think about is you need to consider really learnings from similar deposit types or styles, similar deposit types which have similar mineralogy. And these are really free lessons, so you really need to do your homework. You need to worry about what your final product quality is, no question about it. You need to worry about what the second subeconomic minerals or elements are, because those are future potential revenue streams. You need to worry about the minerals that are likely to upset your various processing units. You also need to consider and quantify the occurrence and spatial distribution of those processed deleterious elements and minerals across your deposit. You need to think about the mineral and textural variability across all grade ranges, not only focusing on grade today, because what's waste today becomes ore tomorrow. And you need to understand the mineral and textural variability and how that actually impacts on metallurgical performance. You also need to think about any other deposit property that may impact on your process, and that means from mining all the way through to closure. You also need to think about how you're going to take all this information and distribute this geomet information across the deposit, but embed it into the mine planning process. And that mine planning process not only includes on how we're going to mine it, but how we're also going to extract it. The most important thing is to remember is that geomet test, unlike process flow sheet development, there are two different things, even though we might be able to use some of the same data. Geomet tests are typically conducted at a standard set of conditions because we're trying to define the effect of ore properties on their response. And we'll pick up that a little bit more a little bit later. We want to be able to rank all the blocks in our resource model, and we want to rank those, have a relative ranking and even an absolute ranking, so that we can choose the best value blocks. And this really is a relative approach, but allow us to, if we're able to link everything back to the block model stage and every block in the block model, that no matter what your mine configuration or your sequencing might be, your extraction sequencing, you'll be able to cater for it. So it's think about all the things that when you have to off-sell your product, what are anything that's going to upset the metallurgical recovery along that way, and consider all grade ranges that you're going to have to worry about, given that life of deposits might be from a few years out to 100+ years. So you need to think across all kinds of time scales. However, when we're doing all this and all of our observations that we have and our data, there's really three real fundamental quantitative relationships we have to worry about. So in geology, we go back and remind ourselves we're excellent at observing, but we have to quantify what we observe. And things that we're taught is that mineralogy is actually a function of the elemental composition of the sample. Yep, we say that's obvious. Some deposits, that's a lot more difficult to do that than others. Things that is slightly different for geologists to understand is that metallurgical performance, and that means all the way from mill throughput, mill hardness, various flotation recovery and acid leaching response, reagents, consumption, smelter throughputs, refinery throughputs, anything that we might worry about in the plant, that the metallurgical performance is actually a function of the mineralogy, the ore textures, and the process conditions. And one thing that has got the industry in trouble throughout its past is that we assume that future performance is actually a function of historical performance. And that might rarely be true, but most of the time it's not, and invariably it gets us in trouble. So on the sample scale, if the first two relationships can be developed for a deposit, then the metallurgical performance can be predicted across the entire deposit. We don't have to test everything across the entire deposit. We can predict it, and it works quite well. So overall things we need to think about for geomet and the importance of mineralogy going into it. So I'm just going to give you some examples from Olympic Dam. The deposit was discovered in July 1975, and it was a new deposit type. First underground access in 1982, production in 1988, and BHP acquired it in 2005. We produced 4 products right now: copper, uranium, gold, and silver. We have always produced 4 products. All mining, and all mining occurs underground, and it's mechanized sublevel open stope mining. And more importantly, is all processing occurs on the surface at Olympic Dam, and we export final products away from Olympic Dam. On the ore body side, Olympic Dam, the IOCG deposit, is a world-class body by anybody's definition. And we're not going to look a lot about the geology, but it's important to see the geological map. And this is a projection at about 350 meters beneath the surface. And the really important thing is that orange dotted line shape in there, that actually is our resource outline. The gray dotted outer boundary is the boundary between fresh Roxby Downs granite and the breccia complex itself, and then the darker gray or the darker shades of gray just represent increasing iron content. The deposit is completely concealed under 350 meters of unaltered cover sequence. The footprint of that breccia complex is about 50 square kilometers. That deposit or that resource outline is really, that's the really important part of it, is it's 6 kilometers down its diagonal, about 3 kilometers wide, about 800 meters depth, but some parts of the deposit, particularly in the south, go down greater than 2 kilometers. and there's an unequivocal spatial relationship between iron, copper, uranium, gold, and silver. The most important thing for predictive power is the deposit-wide mineralogical zonation. We have that for the sulfides. We have it for associated trace elements. Uranium minerals, coffinite, branorite, and uraninite. It's not so obvious. And there's 3 different styles of gold mineralization. But for us, really, it's around the systematic zonation of the copper sulfides and the gangue minerals that go along with that. We can look at Olympic Dam in a nutshell and really say we start with the Roxby Downs granite, so these nice little panels of rock on the right-hand side. And we start at Roxby Downs granite that starts at 3% iron. And as we're progressing from the edges of that breccia complex in towards the center, we're just progressively adding iron and a whole suite of hydrothermal elements while we're wiping out all the pre-existing granite. So we go from a rock that's got 3% iron to 60% iron. Now, the important thing is we look at each of these little panels and we say, oh, those look pretty unique. But what happens, there's a continuum of everything in between there, so there's really no hard contacts. When we look at some of these other colors on the map, the colors, other colors besides gray and that purple, actually represent bedded clastic facies that are inside of that deposit, and they do become brecciated and altered. But the most important one is that conversion of granite to a granite with 3% iron into 60%. When we look at these things, and we're going to look at the diagram on the upper right-hand side, we can plot iron versus the bulk dry density, which is all those orange dots increasing, or iron versus silica, which is the inverse relationship. And what we see is just nice clouds of data that are increasing or decreasing with the iron content. From a predictive power, these are excellent. But when we look at this, we also see there's no significant breaks in there. And that really helps support us with this idea that there's really a continuum going from granite-rich breccias or granites to granite-rich breccias into these barren quartz hematite breccias. We can also plot any kind of other element sequence that we want to look at, but the lower diagram shows sodium versus potassium, and we can look at the alteration from the relatively fresh granite. Outside the breccia complex really represents all those pink dots heading down towards the lower right, where we're destroying the plagioclase. The vector changes direction as we're then starting to destroy or replace K feldspar with cerussite, and then hematite and starting to replace cerussite, and then where there's just hematite left over. A whole plethora of geochemical vectors that you can use. So we know that there's complex breccia textures, but there's simple, predictable mineralogy. At Olympic Dam, we know that there's more than 150 minerals in the deposit, and we continue to find more, particularly as our scale of observation is down now at the nanoscale. Those 150 plus minerals each have its own processing responses and impacts, but you say, how could we possibly worry about 150 minerals? At a very detailed scale, we can't. Fortunately, about 15 of those minerals count for greater than 99.5% of the ores. And the ones that are really important for us are the gangue minerals, which are shown on the right-hand side, but the orange ones shown on the right-hand side. And then the sulfides shown on the left, on the upper 2 lines, and then things like coffinite, uraninite, branorite, and then some of the rare earths. And all the minerals aren't listed here, but they're all there. We need to know about them, and we need to be able to assess them, but to different levels of precision that we have to do. The important thing is to know when we're thinking about geometallurgy, and then my side back to being an economic geologist, a nice quote that I like from Nigel Cook and Christiana Charbonneau is that every mineral has a story. Indeed, every mineral does have a story. And when we need to understand the genesis of the deposits and understand how they're going to recover in a plant, we need to know about them all, but to different levels of precision. So we jump, and then thinking back at Olympic Dam, we know we have this 10+ billion ton resource, and we're going to process that. And Olympic Dam, because we do produce final products, this is an incredibly simplified flow sheet, We start from mining in the upper left-hand side, and we go across, we grind it, we float it, and then we then treat the concentrate and the tailings. And the concentrate stream, we leach it, we smelt it, we produce an anode, then we produce ER copper, and then ultimately gold and silver bullion from that. The tailing stream, we actually do a sulfuric acid leach. We extract some uranium and a little bit of copper left over. We extract the bulk of the uranium. We have to separate that uranium from copper in solution. It goes into copper SX and uranium SX. The copper then goes into EW, where we make an EW cathode, and that gets exported. We make an ammonium diuranate, which is true yellow cake, that gets roasted to make uranium oxide for transport. And I have that shape around the sulfide flotation. Most ore deposits or most mines in the world, metalliferous mines in the world, their problems stop at that sulfide flotation because they make the sulfide con and they ship it someplace else to be treated. That's only the beginning of our process at Olympic Dam. So we say, people ask me, what are your different ore types? And I'll say, okay, ore type, we actually don't classify our ore body based on single sets of ore types. So we're just going to bear with me for a minute. So we say at Olympic Dam, given that whole process stream, what's the perfect ore for Olympic Dam? And it all depends. So geologists not only use this term, it all depends, but metallurgists use it also. And it all depends. It depends on what part of the plant you're in, on what components in an ore are good or not good for them. So the smelter, you'll see a certain set of criteria: comminution, tails leach, flotation, refinery, and you see all different sets of criteria. So if we take all of those and you try to come up with very specific ore types, we would easily come up with more than 100 ore types, and that's actually not practical. So we had to do something different at OD. The first thing you do is we go back to the original definition from Steve Williams about the ore characteristics. And we need to identify the process drivers that are affected by ore characteristics, not the process conditions. So mill throughput, it's all about ore hardness. And for us, that means hematite, quartz, sericite, plus other gangue minerals a little bit. And we also need to think about the sulfide grain size, because how much you grind, grinding is all about liberation, and the sulfide size dictates on how much you're going to have to grind, or how much you're going to have to grind. When we go into flotation performance, the reason for flotation is to separate the revenue stream, or sorry, the sulfides from the gangue minerals. But for sulfide flotation, it's really about the concentrate grade and quality. So that means for us, it's sulfide recovery, the sulfide minerals, and we use a copper sulfur ratio as a proxy for those sulfide minerals, but we can easily predict them all and we measure them. And it's really about their association with the gangue. We also have to worry about deleterious elements in the copper concentrate, and these are just a few of the elements there. There's a lot more of them around, and those things are all available off of concentrate specification sheets. Tails leach and uranium recovery, the things that impact on flotation recovery actually don't have a lot of impact in tails leach or uranium. For any tails leach, or even if we were on a heap leach or any other kind of leaching, it's really about acid consumption. And when we're doing rapid leaching, we have to worry about gelling potential. Uranium extraction, though, is strongly dependent on the uranium mineralogy, because each of our uranium minerals have different abundances of uranium in them, and they also leach at different rates. We have to worry about their grain size and what those things are locked in. In a tails leach circuit, or even in a flotation side, in metallurgy, we actually have to separate the liquor from the solids eventually. And micaceous minerals, which includes clays, have a propensity to cause solid liquid separation. So we actually have to worry about those minerals. And the copper extraction that we do get out of there is dependent on the sulfide mineralogy. And it's a small component, but easily predictable. When we're in the smelter and refining areas, we have to worry about smelter throughput. And smelters, besides making blister, which is blister copper, they also have off gas, which is SO2 emissions, and they have to deal with slag and the refinery. We've lumped it all together. But things that impact directly on smelter throughput, off gas and slag handling is the sulfide mineralogy and the concentrate grade, and really the non-sulfide gangue mineralogy too. The big thing that impacts on the refining is all these other trace elements that occur in there that can impact on your quality of your copper cathode. And these are elements like arsenic, bismuth, antimony, selenium, and tellurium. These are things that are different for every plant, and depending on what your plant configuration is what elements and minerals you really need to focus on. But even though we might only focus on what appears to be 15 sets of minerals in there, we also monitor concentrations of about 60 elements, 65 elements from drill core through final products. That helps us keep an eye on additional revenue stream, deleterious elements, and any things that might have any HSEC implications, et cetera, and the list just goes on and on. What do we do with our material? And we think from a deposit scale, and we think at Olympic Dam, you know, this massive resource model, and there's no way that we can ever have metallurgical testing that's even within several orders of magnitude of numbers that happens within our resource model. So we actually have a real kind of tiered approach to our sampling. Our resource drill hole database, our resource drill hole assaying database, is probably the most extensive database that you have across the site. So we really had to enhance it. And for us at Olympic Dam, we have about 2 million assayed samples, of which those greater than 2 million assayed samples, we have over 26 elements that are in there. We have density, magnetic susceptibility, and all kinds of other geological and geotechnical logging information. We very precisely calculate the mineralogy of 50, or the concentration of 15 minerals in there on every single assayed sample. So by having those assays backed up by a lot of measured mineralogy, we also have 2 million samples that also have these calculated mineralogy with them. So we think about that 2 million samples, then we're going to go down to what we call our ore characterization samples. And for us that's at least 2 orders of magnitude less samples than what we do for the resource side. But here is where we start doing a full expanded suite of elements, so everything we possibly can. We do measured mineralogy on all those samples. That means a full automated suite, like MLA mineralogy. And then we also do simple things like quantitative XRD. And what that does is it allows us to confirm this relationship that we have, that the mineral weight percent is a function of the sample composition, but we continuously validate that because we heavily rely on that relationship. So now we're going to say, well, we haven't talked about any metallurgical testing yet. Metallurgical testing is our next frame that comes down. And our geomet testing is then another 3 orders of magnitude less samples than what we started with. And we have about 2,000 samples, again, scattered across 6 kilometers of ore body, or of 6 kilometers of resource model, where we have full metallurgical testing. That means comminution test, rougher, cleaner flotation, multiple leach tests. From there, we do very specific ore characterization tests where we have mineralogy and assaying on all the samples on a size by size basis. But we do the same test that we do for those ore characteristics. That allows us, again, to link the mineralogy as a function of sample composition back to those ore characterization tests, which then allows us to validate back to our resource model. We also, at that point, come up with our metallurgical performance parameters as a function really of the mineralogy ore texture, and not the process conditions, because we've held those constant. And that's important because we go back to think about the number of samples that we're doing, from a few samples, about 1,000, about these 2,000 samples, and eventually propagating all that information up to 2 million assayed samples. We can't do geomet testing at the same scale that we do drill core assaying at. One of the most important features that we have for Olympic Dam is that we're able to assign value to every single resource block in that resource model. For Olympic Dam, that means that we have over 50 geomet attributes, which allows us to do a high level metallurgical balance across the entire plant. And the image of the really even smaller version of the plant is what's on the lower right. We have to express our various metallurgical recoveries as functions of variables that are in that resource model. So that means we have to express them as functions of the minerals, elements, density, mag-sus, which are all geostatistically estimated into every single resource block. Our geomet attributes are calculated on each block post the estimation process. And this gets around the problem of additivity that you often have for physical properties, that most physical properties are not additive, and that gets us into problems. And so that's why at Olympic Dam that we actually base everything back on the minerals and elements, which are additive within a resource, and we can do proper geostats on that. Value from all of this, true value can be assigned to every single block. And that then is used in mine planning, whether you're looking at short-term, like 2-year plans, 5-year plans, life of asset plans, or even back at the early exploration stages where you say, I got interesting mineralization or have an interesting volume in it. Mining engineer, what might you do with that? And then metallurgist, what might you do with that kind of configuration? We have the ability to sort all these little blocks around no matter what our ultimate outcome is going to be. So as geologists, we live in a, historically, our observations are very qualitative. We like to think that they're quantitative, but they're certainly not. Our block model is really a discretized version of that beautiful geological map that we see with all kinds of other things in it. Our resource block model actually has 20 million blocks in it. Those block sizes vary from 5 by 10 by 5 up to 30 by 30 by 15, depending on what the sample spacing is. And it's fully supported by greater than 2 million assayed samples. Each block has all those elements in it and those process critical minerals, plus these 50 geomet parameters that are on there. So beautiful geological map, but that geological map is not of use to the business. That discretized version of what we observe geologically and what we test is actually what the business can actually utilize. Jess, how am I doing with time?
It's all good. Yeah, it's nearly 4:45.
Okay, so I'm very close to the end here. So some of the products that we actually make from these things, and we think about geological maps that we see, where often we might talk about a certain sulfide being more, or most of our maps actually will have a mineral specific dominance, but we can make maps, whether they're discretized things or nice block model slices, and these are all slices at one consistent level, where we talk about what the absolute weight, what the absolute abundance is of bornite, chalcopyrite, pyrite, or even copper across the deposit. And I should say these have been rotated from geographic north by minus 57 degrees, so that a mine planning grid is what the north is on there. And the first thing we see is there's a lot of variation in colors, and each of those variation in colors is not a mineral a dominance, it's an absolute mineral abundance. Whether it's the sulfide minerals or our gangue minerals, hematite, quartz, sericite, we see a lot of changing patterns. Yes, that's what's actually going on. It's fantastic to look at these. We can also look at the variation in important gangue minerals like siderite, fluorite, barite, changing from the edges of the deposit going towards the center and how that relates to copper mineralization. We can also look at it at a different scale. So on the left-hand image shows arsenic in the ore body, variable across it, and that's actually almost counter to what's going on with copper. That middle diagram just shows you what our life of asset stopes are and broken down into different mine areas. And what we can see on that diagram on the right-hand side is it goes really, the left side is top of the ore body going across that diagram to the right, which is really the southern part of the ore body. And just looking at the range, or you look at the box and whiskers of going across that ore body from north to south. And we see quite a variation in something called arsenic, and that's still not bad arsenic concentrations. But what's more important is not what the absolute concentration of arsenic is, how it actually recovers to that concentrate, which means ultimately how it might end up over in copper cathode. We see big variations, but there's spatial systematics to that. And the big two bars that we see on the right-hand side, besides there just being more grade there, but the arsenic mineralogy, along with a whole other suite of elements, is very different in those two mine areas than it is in the rest of the ore body, which also means that there's very difference on how it's going to recover. So grade is not the only indicator. You also have to understand how your mineralogy and how that grade changes with mineralogy as the grade actually changes, which is kind of almost circular discussion. So I think I'm going to skip these next two things here, and they're available in the presentation. It just talks a little bit about how we've developed our simple bond work index, which is the indicator of hardness going through the mills, and what that distribution, so we can even distribute all of our different metallurgical parameters, and we can see what the hardness is over on the side. And what I want to do is just jump to the summary for Olympic Dam. That Olympic Dam, we've been very successful at quantifying the mineral weight percent as a function of the sample composition, which then allows us to quantify the metallurgical performance really as a function really of mineralogy and assays. When we were able to do that, it was transformational. We could actually do the geomet that we were supposed to do. But it took actually a decade of us working on it to do that, from really about the mid-1990s up to about 2005, and even a little bit later than that. We're able to quantify our geological observations, which are critical, populate the block model with mineralogy, more critical, conduct metallurgical test work on variability samples, and that's really important, variability, not composites, develop predictors of metallurgical performance, and we can include the mineralogy and performance in our mine plans or production schedules. And once we're in an operating environment, the business value can only be realized once the observations and data are in a plan or a schedule. So we'll just do a very quick quiz, and I can't see faces, so we'll just kind of jump through this. And some of you might have seen this before. How many minerals are there? And we might hear somebody screaming in the background, and Jess will tell me that people are giving us some numbers, perhaps off of the chat side.
150.
Yeah, for Olympic Dam, how many minerals are known throughout the world, we'll say?
Oh, in the world.
Yeah, sorry.
5457, 1 billion.
There you go. Somebody's actually read it, one of my old presentations, but 5780 as of January this year from the International Mineralogical Association, but a lot, okay? A lot of minerals around there. How many of those minerals do we actually need to know? You know? And then, so you're going to tell me, Jess, that everybody's saying
10.
That's
Changes
probably pretty damn good. Sounds good. No definitive answer.
All of
it depends on your deposit. Yes.
The ones that have value.
Well, that's right. That's even better. It depends on your deposit and your metal extraction process. But with all of those ones, you know, those plus 5,000 minerals that we know that nature is kind most of the time, that we're never going to see all those in one deposit, that each mineral deposit type is usually typified by a characteristic suite of minerals. You know, we know that. There's often more than 100 minerals in most deposits, even though we usually worry about less than that. But as a minimum, what we need to worry about are the ones that are going to impact on our process or our final products. You know, it's our revenue stream. So everybody did incredibly well at that quiz, I'm sure. So for final conclusions, you know, mineralogy, it's key to unlocking value in our deposits. The way we used to classify deposits or characterize deposits in the 20th century is no longer how we do it in the 21st century. And a lot of people will say, well, Kathy, everything you described, only somebody with the mind of BHP can do something like that. And I'll say that's absolute nonsense. That we can do a lot better job on any deposit they're working on thinking about how we can quantify that mineralogy. Not necessarily at the scale that we've had to do at Olympic Dam, but it's possible for everybody. We must estimate or measure the mineralogy at the deposit scale by a method appropriate for your deposit. And as geologists, we need to understand how their deposit mineralogy impacts on final products and actually the waste streams too. We need to get the mineralogy and metallurgical data into models, into resource models, so they can be as inputs into mine planning. And one of the things that we don't do well with geoscientists, we love to use our highly descriptive language that most metallurgists don't understand. And my metallurgical friends call it our geological gobbledygook that we create words, but we need to more effectively communicate with non-geoscientists within the with non-geoscience disciplines within our business. And the better that we get at telling a metallurgist, not telling him very advanced argillic or propylitic or any of that. Some of them actually understand them, but if you tell them most of the minerals in it, they understand that far better than if we use a description of what the alteration happens to be, or our alteration words that we use. But the most important thing as geologists, from exploration all the way up to production ones, is that metal has no value until it's a sellable product. And again, that's another quote from Bill Johnson and Peter Monroe. And it's really important that early on, we can get very excited about a few meters of 0.2 or 0.3% copper. Well, really? We really just need to think of the scale. And my final word will be just looking at the picture. This is an old picture at Olympic Dam. The core processing area, we have about 3 million meters. It's now scattered between a couple different sites, but a geologist dreamed that we actually keep all the core that we've drilled from day one at Olympic Dam. So Jess, I'm going to say thank you for the attention, and we can open it up to questions.
Thank you so much. That was amazing.